Welcome everyone to our lecture today in fuzzy systems. Today we are going to have an application on defuzzification methods. As we explained before, defuzzification methods are used in order to convert a fuzzy quantity into a crisp classical quantity. So instead of using a range of values as given by fuzzy quantities, we simply express our quantity as an absolute value as given by classical and crisp sets. So this time we are going to apply our 7 defuzzification methods. We have here in this example 2 fuzzy membership functions which are shown as trapezoids, and it is required to determine the defuzzified output value by all the possible methods. So first we have to write down the equations describing these membership functions. We have here the 2 trapezoidal membership functions. The first step is to write down the equations which are shown here as straight lines. So we have here a11 for this straight line, a12 for this straight line, and a21 for this straight line, and a22 for this straight line, and a23 for this straight line. So we have 1, 2, 3, 4, 5 straight lines in which we are going to express them using straight line equations. It can be noticed that this straight line is not needed because it lies in the overlapping area between the 2 membership functions. So for the first straight line a11, the points are 0, 0, 0, 0, and 2, 0, 7. This is 2, here 2, and the height is 0.7. So we simply write down the equation, which is y minus 0 divided by x minus 0 is equal to 0.7 minus 0 divided by 2 minus 0. So by cross multiplication, in this case y is equal to 0.35 multiplied by x, such that 0.35 is the slope of this straight line. For the next one, a12, which is this one here, the straight line is equal to y equal to 0.7, which is the height of this straight line. a13 is not needed. As we said before, it lies in the overlapping area. And a21 has the points 2, 0, and 3, 1. So the straight line can be expressed as y minus 0 divided by x minus 2 is equal to 1 minus 0 divided by 3 minus 2. So by cross multiplication, y is equal to x minus 2. For the straight line a22, simply y is equal to 1, and a23, which is noted by the points 4, 1, 4, 1, yes, here, and 6, 0, 6, and 0. The straight line can be expressed as y minus 1 and divided by x minus 4 is equal to 0 minus 1, 0 minus 1 divided by 6 minus 4. Simply by cross multiplication, we get EY is equal to minus half multiplied by x plus 3, where minus half represents this negative slope of the straight line, and 3 is the point of intersection between the extension of this line with this mu axis. So we simply solve for the two equations of A11 and A21 in order to find out this common point. We solve for the two equation A12, yes, this line, and A21 in order to find this intersection point and to determine accurately the x point of this intersection point on the z-axis, which is 2.7. So by solving these two equations, we find out the value of x, which is 2.7. This represents this point. After that, we have here all the unknowns and all the equation describing our membership functions. So we apply the first method here, is the centroid method. And as we mentioned, the centroid method is equal to this integration of the membership function multiplied by z dz and divided by the integration of the membership function multiplied by dz. So we take the numerator at first and substitute with all the available data we got. So for the first part, we integrate simply this function of A11 with the limits from 0 to 7. From 0 to 2. From 0 to 2, and write down the equation of the straight line A11, which is 0.35 z, and we multiply by z, so we got this z square plus 0.7, which represents the equation of the straight line A12 multiplied by z. The limits of the integration is from 2 to 2.7 plus this part here, which has the equation z minus 2, and the integration limits are from 2.7 to 3. Multiplied by z. For the next part, a to 2, the integration limits are from 3 to 4, multiplied by z. For the last part, simply the equation of the straight line multiplied by z. The limits are from 4 to 6. So simply put here the limits of the integrator and solve this equation algebraically. We got at the end that the defuzzified value is equal to 10.977. For the numerator, we simply repeat the same step but without multiplying by z. So we put by the same way the limits of the integrator from 0 to 2 in the first straight line, and for the next straight line from 2 to 2.7, and for this straight line here is from 2.7 to 3, and from 3 to 4, and from 4 to 6. Simply substitute with the values of the integrator limits. We got at the end this value. So the defuzzified value z star is equal to the numerator value divided by the denominator, which is equal to 3.18. 3.18. Okay. The next method is the center of sums. In the center of sums, we apply simply this rule. And in this rule, we get directly the area of we got the area of the membership function multiplied by z bar, which represents the centroid or the center area, the center distance of the base of the membership function. So we have here for this membership function A1, z bar is equal to 2, and for the second membership function z bar is equal to 4. So for the first membership function, the area is equal to half multiplied by the summation of the two bases of the trapezoid, which are 4 plus 1, multiplied by the height, which is 0.7, plus half multiplied by the summation of the two bases, which is 4 plus 1, multiplied by the height, which is 1, multiplied by z bar, which is half the distance, which is the value at half the base of the trapezoid, which is 4. So we, after calculating the value of this fraction, we got the defuzzified value 3.176. The center of largest area method, we simply get the area of 1 and 2. Area 1 is limited at this dash line, which passes through the intersection point between the first membership function and the second membership function. Area 1 is equal to the area of this trapezoid here, which is half the summation of the two bases, 2.7 plus 0.7 multiplied by the height, which is 0.7. We multiply this area by 0. Which is equal to 1.19. For the second area, which begins from this dashed line, we calculate the area such that we represent this small area here as a trapezoid and add it to the trapezoid next to it. So the first small trapezoid is simply equal to half multiplied by 1 plus 0.7. This is 1, and this is 0.7 multiplied by the height, which is this small distance 0.3, plus the area of the trapezoid here is equal to half multiplied by 3 plus 1. Here is 3, from 3 to 6. This is 3 plus 1, which is this distance, multiplied by 1, which represents the height of the trapezoid. So this is equal to 2.255, and we see here that 2.55 is greater than 1.1, so area of 2 is greater than area of 1, and by this we consider only area 2 for calculating the defuzzified value Z star. So this area 1 will not be considered and area 2 will be considered. So Z star in this case, simply apply the centroid method we have explained before by subdividing the membership functions into definite straight lines and then calculate for each region the integration. Okay, for the first region, z minus 2 multiplied by we simply begin from here. So this is our straight line. So the limits of the integrator is from 2.7 to 3, and this is the straight line describing this is the equation describing this straight line. The second region is from 3 to 4, from 3 to 4, and the third region is from 4 to 6. The same is written down in the denominator, but without multiplying by z. Simply substitute with the integrator limits in both numerator and denominator, and at the end the defuzzified value is equal to 3 point. The min max method is simply got by taking the mean value of the maximum. Here the maximum lies in the range 2 and 3, So the mean is 2.5, and here the maximum lies between 3 and 6, between 3 and 4. So the mean here is 3.5. We add them together and divide by 2 to get the mean max value, which is 3. First of maximum is simply here because it is at 3, and last of maximum because this is the highest values for the two membership functions. So last is at 4, so z star is equal to 4. The weighted average method can not be applied due to asymmetry because we can't bisect these membership functions. The maximum membership function lies between 3 and 4. We are now at the end of our lecture. Thank you for your attention.